So this last lecture on limits, I want to revisit the first lecture, which was on continuity and limits. So I've titled this basically Limits 3 on YouTube, but it's really sort of going back and looking a little bit deeper into continuity and limits. So let's talk again about what is continuity. Now we explain this to people by saying a function is continuous if you can draw it without lifting your pen or pencil, and it's not continuous. So let's draw a function that's not continuous if you have to, let's put a jump right here, if you have to lift your pen or pencil, or you could have an asymptote here. That's my asymptote. And it's also not continuous there. But what we really mean by something being continuous, the actual definition of continuity, so we define f of x to be continuous at x equal a if it satisfies this condition, the limit as x goes to a of f of x is equal to f of a. So this is really the key statement, and this is the essence of continuity. And what it really means intuitively, I mean, there's the picture, but when I look at the limit, I think it means my best guess, because that's what I think of the limit. It's sort of like my best guess. I look at values from the left, I get a number. I look at values from the right, I get a number. It is equal to the actual value of the function. So your best guess is spot on, basically. Let's look at an example. Okay, so here I want to use the definition of continuity to prove that a function is not continuous at x equals 3. So the idea is I want to look at this limit as x goes to 3 of f of x and see, is it equal to, question mark, the actual value, f of a. If it is, it's continuous. If it's not continuous. And now the problem with this at 3 is you have this sort of piecewise defined function. When it's less than 3, you use this piece, whereas when it's greater than 3, you use the bottom piece. So what you're going to have to do to determine if this limit even exists is you're going to have to look at the limit from the left. So the limit as x goes to 3 from the left of f of x, which is equal to the limit as x goes to 3 from the left. Now, if you're coming in to 3, so think of the number line. Here's the number 3. If you come in from the left-hand side, these are numbers that are less than 3. So I'll use the top piece. So this is going to be then 2x minus 1 because I'm coming in from the left of 3. And I simply plug in the point, 2 times 3 minus 1, and I get out 5. So there's a limit from the left. And then the limit from the right, the limit as x goes to 3 from the right of f of x is going to equal, and I copy down the limit as x goes to 3 from the right. Now I'm coming in from the right-hand side over here. So these are numbers that are actually bigger than 3. So these are numbers that are bigger than 3, whereas from the left, it's things that are less than 3. So for bigger than 3, use the bottom piece. So I'll use x plus 1. And so that's equal to 3 plus 1, which equals 4. Therefore, so we use these little 3 dots to mean therefore the limit as x goes to 3 of my function f of x is equal to, and we say it does not exist because, well, we could say 5 is not equal to 4. Really, that is to say that the limit from the left, right, the left-hand limit, is not equal to the right-hand limit. That's why the limit does not exist. Right, so that's how you prove something is not continuous in all its definitional glory. Okay, so to understand continuity, you have to understand limits. Okay, so what is a limit? So again, I talked about this intuitively. It's sort of like you're looking from the left, you're looking from the right, you're going to see what happens. So here's a function here. Let's say it has an open circle at height 1 over at 2, and above it up here at 3. Okay, you close the circle and it goes on like that. And so if you look at the limit as x goes to 2 of f of x, if this is our function f of x, we say this does not exist. Because my best guess from the left would be 1, my best guess from the right would be 3. Those two guesses don't coincide, and so we don't have a best guess basically. So we say that limit does not exist. Of course, the definition, which I gave you in a previous video, doesn't seem to imply that at all, but it actually does when you start to really work with it. So let's look at the definition again. Let's start to work with it to see if we can become a little bit more comfortable with this thing. So here's a definition, and I took this right from your book. We say that the limit of f of x as x approaches a is L, and here's what we write, what we've been writing. If for any epsilon bigger than 0, we can find some number delta bigger than 0, such that if we have this case, which is just basically saying the distance from a is less than delta, then the distance of the function from L is going to be less than epsilon. And so here's a picture down here below it. And the idea is if you give me an epsilon, what I can do is I can look with inside this region, L plus epsilon to L minus epsilon. And then what I want to come up with is some delta, so that if I look to a little bit to the left of A, so delta to the left of A and delta to the right of A, that the actual graph that corresponds to those inputs will be within that sort of region here they shaded into blue. So here's an example over here. So let's take a look at this example. It says use a given graph of f to find a number delta such that if the distance away from 3 is less than delta, then the distance away from 2 is less than 0.5. And so over here they gave you sort of this region 2 plus 0.5 and 2 minus 0.5. And over here they found the corresponding input. So if you have 1.5, this input is 2.6. If you have the output of 2.5, this input is 3.8. And we want to find a delta so that we always wind up within this part of the graph basically. And so if you think about this, look over here, you have a plus delta and a minus delta. So you basically have two choices for your delta. This distance from here to here is 0.8, whereas the distance to the left is 0.4. And so you can choose your delta to be one of these. If you choose 0.8, you'll be wrong because 0.8 will go outside here on the left-hand side. You know, 0.8 will take you all the way down to what, 2.2? So that's too big. So 0.4 is just right. If you go 0.4 to the left, you're still within this region. And if you go 0.4 to the right, you're right here at 3.4, so you're still within this region. So you'll be basically on this, above it, you'll be on this red part of the graph. So my delta will be 0.4. So as long as the distance from 3 is less than 0.4, you'll be good. Your distance from 2, your outputs, your distance of your outputs from 2 will be less than 0.5. Right, so let's say that again. These are inputs, these are outputs. So if the distance of your inputs from 3 are less than 0.4, then your distance of your outputs from 2 will be less than 0.5. And you can see that from the picture. The distance is less than 0.4, you're going to be within here. And if you look up, here's your graph, and so you're certainly within 0.5 of 2. Let's look at another one. This one's going to be a little bit harder because they did not give us the inputs. We're going to have to find them, but they actually gave us the function here. So use the graph of the function f of x equals x squared to find the number delta such that if this is true, the distance of your inputs are less than delta, then your distance from your outputs to 1 is less than half. Okay. So first thing I'm going to do is I'm going to find these question marks, and so I'll need a calculator. So where's my calculator? Here's my calculator. So I'll pull that up. And to find my inputs, well, I know if I take this question mark right here, if I take this question mark and I square it, I should get 0.5. So question mark squared will equal 0.5. Whereas this other question mark right here, oops, I want to use a different color. This question mark right here, different number. If I square it, I'm going to get 1.5. And so what I can do is figure out the square roots of these with my calculator. So take second square root of 0.5, and that's going to give me this number. And so I can write down in red this answer. So question mark is going to be equal to 0.707. 106. I'll just copy it all down. 7812. And then in blue, I'll take the second square root of 1.5. And so this is going to equal, and let's change the color to blue. So this is going to be question mark is going to equal 1.22. And then I have 4744, and then finally 871. Great. So those are my two question marks. And then the question becomes, how far away is it from 1? So let's figure that out with the calculator. Let's do this one first since I have it up. So I can take away 1 from that answer, and I get 0.2247. And I'm just going to do this to, let's do this to 4 decimal places. So this is going to be, this distance here is going to be 0.2247. Whereas the distance on the left-hand side, I can figure this one out by, again, taking the second square root of 0.5 to write down that answer. So there's that 0.707. And its distance from 1, let's take 1 minus the second answer, is this number, 0.29, and let's do 29. So 0.2929. So that's this distance here. And so if I'm going to go find my delta, I have two choices for delta. I could let delta be this distance, 0.2929, or I could let it be 0.2247. And I want to take the smaller of the two, because if you take the bigger one, this red distance here, if you put it over here, it's going to reach outside this sort of region you want to be in. So it's actually going to be this one, and it says do it to 3 decimal places. So I'm going to write down for delta 0.225. Because it says round your answer to 3 decimal places. Personally, I think that's a little bit too big, because you notice 0.225 reaches outside the region. So if I was actually doing this question, I'd probably just put 0.22 down, because I know that won't go outside the region. Or I could even put 4 down, but that actually will go outside the region on the right. It's not a big deal if you understand the idea, though. Okay, let's then do one more of these. So I did use the definition of a limit to prove that this limit is actually equal to, in this case, 33. On another lecture, I did a similar problem, but let's do it again so you can kind of see how this proof works. I always tell you guys, I'm not going to test you on this. It's more of a sort of an enrichment activity. And when the time comes and you've progressed mathematically to a point where you can actually do this on your own, then you'll be sort of tested on. But it's a good exercise, I think, to kind of go through. All right, so the idea is you want to be given an epsilon. So you say, okay, let epsilon greater than 0 be given. So the idea is you give me some sort of epsilon, and then we have to figure out what delta is, and take delta to equal. Now, I'm going to kind of pull this out of nowhere, and you'll see where it comes from in a minute, but I'm going to take epsilon over 5. All right, so then if we have 0 less than, now I'm just copying it down, so I found my delta, and now I'm going to take this statement. I'm going to assume this is true. So if 0 is less than x minus, now I have to figure out my a. Well, here's their a, and so my a is 7. So x minus 7 is less than my delta. Then what can I say? Then I'm going to copy down this statement. So they have this f of x here. Now this is the f of x, and so my f of x is 5x. So 5x minus, and of course here's their L, which is equal to L. So my L is 33. 33. Oops, and I forgot the 2. That's going to be important because I'm looking at this, I'm saying it's not going to work, right? So my function is not just 5x, it's 5x minus 2. So change that, 5x minus 2. And then we have minus, and here's the 33. Otherwise, this problem won't work out right. So 33, because the limit won't be 33. And so this is equal to, so combine like terms. So let's combine the constants. So minus 2 minus 33, so that's a minus 35. Oh, and what's nice about that is they have 5 in common. They have 5s in common, so I'll take out a 5. So x minus 7. And it's absolute value, so I can write this as 5 absolute value of x minus 7. And now I know something about x minus 7. I know the absolute value of x minus 7 is less than delta here. So what I can do is write over here that this is less than 5 times my delta. But that gives me, and this is equal to then, that's equal to 5, and delta is epsilon over 5. And so now the 5's cancel here, top and bottom, and I just get simply epsilon. So therefore, what have I just shown? I've shown if I have this, so if I have this, then there's this, there's this. Is it less than that? Where's the less than sign? Here's a less than sign. It's less than that. And so I can conclude, so let's make the conclusion. Therefore, the limit as x goes to 7 of 5x minus 2 is equal to 33 by definition, right? By the definition of the limit. But we can just say by definition, the limit's implied. So this is something to sort of work towards understanding. You know, you can try lots of these simple sort of limits on your own and see if you can come up with a little proof. This, you know, divided by 5 comes right here. A lot of times when we do this, what you'll do is you'll kind of leave this blank. So you kind of leave it blank, and you work through all this, and you get right here, and then you realize that, oh, you need to make delta equal to epsilon over 5, because then when you multiply by it, the 5's will cancel. So at this point, usually, when I'm doing this proof is when I actually go back up and I say, okay, yeah, delta is going to be epsilon over 5. All right, last, so a couple more things. So we covered the definition. I always like to go through these limit laws. All right, so the limits have certain properties, like they go through multiplication, they go through addition, they go through subtraction, they go through multiplication down here and division. They even go through composition given the right conditions, but we're not going to talk about that. But we're just going to talk about the fact if the limits exist, so if this limit exists and this limit exists, then what can we say about limits when we multiply a function by a constant? Well, the fact is you can pull the constant out in front. What can you say about taking limits when you add two functions? Well, you can take the limit of the sum, or you can take the sum of the limits. How about subtraction? Right? If you take the limits of a difference, you can take the limit of the difference, or you can take the difference of the limits. How about multiplication? Right? You can take the limits of the multiplication, or you can multiply, implied there, the limits. And how about division? Well, you can take the limit of when you divide, or you could divide the limits, as long as the bottom limit is not equal to 0, right, which would make it undefined. So as long as these limits exist, you can do all kinds of basic algebraic operations, addition, subtraction, multiplication, division, and even composition, although I didn't put it on here because we're not going to use it. But you should be aware that you can do it with composition too. So let's look at an example. And this is more of an exercise in trying to get your brain to understand what's sort of really going on here when you do limits. So the limit as x goes to 2 of 3 f of x, all divided by 2 g of x minus f of x. So this is sort of a fun little game. The idea is you know that two limits exist. So you know this limit exists and that limit exists. And what you want to do is try to apply these rules, and you can't move to another step unless you apply the rule, one of these rules, correctly. And so like for the first step, I want to write equals, and I have to think, okay, which rule am I going to apply first, 0, 1, 2, 3, or 4? And you have to apply the rule that applies to everything. And you'll look here and you'll say, well, I'm not going to apply the constant times a function because that only applies to the top. I'm not going to apply the rule involving the difference over here too because that only applies to the bottom. But if you think about it, rule 4, this division, taking the quotient of these two functions, involves both the top and the bottom. So I can apply that rule there. So what I'll do is I'll say by rule 4, what I can write is that this is actually equal to the limit of the top divided by the limit of the bottom. So divided by the limit as x goes to 2 of the bottom. So 2 g of x minus f of x. And then we keep on going. So now what am I going to do? Well, in the top part, I can use this rule 0. So I'll put a 0 here on top. And then on the bottom part, what can I do? Well, I'm not going to use rule 0 because that applies only to the first term. I'm actually going to use rule 2 right here on the bottom. So I'll just put a 2 down here on the bottom. So I'm telling the reader, whoever's looking at this problem, exactly what I'm doing. So rule 0 says I can write this as the limit, 3 times the limit as x goes to 2 of f of x, because it basically says if you multiply by a constant, you can pull it out in front. And then all divided by the limit as x goes to 2 of 2 times g of x minus the limit as x goes to 2 of f of x. And I'm just using rule 2 here. It basically says the limit of a difference is the difference of the limits. So here's the limit of a difference, and this is the difference of two limits. And then we can do one more line here maybe. So this is equal. So let's clear up just the last part because after that I can just plug in the numbers. So this is going to equal, by rule 0 on the bottom, I'm going to have 3 times the limit. This is the same. This doesn't change. X goes to 2 of f of x. Then divided by, on the bottom I can pull out that 2 now by rule 0. So the limit as x goes to 2 of g of x minus the limit as x goes to 2 of f of x. And now I can just simply plug in the appropriate numbers because I know everything here. So here's f of x, here's f of x, right? So the limit as x goes to 2 of f of x is 3. And of course, for g of x, we know this limit is 7. So we plug in a 7 right there. So let's just plug in the numbers. We'll be basically done here. So this equals 3 times 3, because that's what the limit is there, divided by 2 times 7, because that's what the limit or g is, and then minus a 3. And so this is equal to 9. Almost want to write 6 there. 9 divided by 14 minus 3. And so this is 9 over 11. So the idea behind this problem is try to justify each step of taking the limit. Now I know you can just plug in a 3 here, and you can plug in a 7 here, and plug in a 3 here, and get out 9 over 11. That's not the point. Right? The point is to understand that there are certain laws for limits, that they basically go through addition, they go through subtraction, they go through multiplication and division, and you can use these laws to justify why the limit is actually 9 over 11. So one last thing I want to cover, it's called the Squeeze Theorem, and let's just take a look at the example we're going to do. So the Squeeze Theorem basically, and this is sort of a powerful theorem, and you use this in all sorts of area of mathematics. The idea is if you have a function f of x, right, so let's say if we have this function, if g of x is less than or equal to f of x, which is less than or equal to some other function h of x, right, then basically what we can say is that the limit as x goes to a And let's assume these limits exist. Let's assume all limits exist, okay? So the limit as x goes to a of g of x should be less than or equal to then the limit as x goes to a of f of x, and should be less than or equal to the limit as x goes to a of h of x. All right, so we'll assume this equality here, this inequality holds for all values of x, and that the limits as x go to a exist. Then, by the squeeze theorem says this inequality will hold too. So let's take a look at the problem. What we want to do is use a squeeze theorem to actually prove this. And so what you want to do is you want to basically bound this function, x squared sine of 1 over x, between two other functions. So let's do it like this. So notice what? If you give me x squared sine 1 over x, this is always going to be less than or equal to x squared times 1. And you just write x squared. Why? Because the sine of 1 over x is always less than or equal to 1. Because that's how the sine works. It goes between the values of positive 1 and negative 1. Oops, that's the cosine. So let's take that off there, right? So it's always less than or equal to 1, and it looks like this. Always between negative 1 and positive 1, and repeating every 2 pi. So that's on that side. And of course, on this side, it's always bigger than or equal to than negative 1. So over here, I could put this is going to be greater than or equal to x squared times negative 1, which would be a negative x squared. So what I have done is I've squeezed this function in between negative x squared and x squared. And now I'm going to apply the limit. All right, so then we can say, thus, by the squeeze theorem, what do we have? The limit as x goes to 0 of negative x squared is less than or equal to the limit as x goes to 0 of x squared times sine of 1 over x, and that has to be less than or equal to the limit as x goes to 0 of x squared. And the limits on the left and right I can evaluate. These are nice continuous functions. So remember, for a continuous function, you simply plug in the point 0. So if you plug in 0, you get out 0 squared, which is 0. And so that'll be less than or equal to the limit as x goes to 0 of x squared sine of 1 over x, which is less than or equal to, and now this number here, this limit, is also going to be 0 because x squared is continuous, so you can plug in 0 and you get a nice number 0 out. So 0 is less than or equal to something is less than or equal to 0, so something must be equal to 0. So therefore, the limit as x goes to 0 of sine, x squared, right, sine of 1 over x is equal to 0. And so that's the idea behind this squeeze theorem. You take a function, you squeeze it between two things, you apply the limit, and the limit on the left goes to a number, the limit on the right, hopefully, if you chose it right, maybe it goes to the same number, and then you've squeezed that middle function in between these two limits, which are the same, so that must be the limit. So this is just what we covered. Like just a real quick sort of overcap. You know, we talked a little bit about continuity. The real significance of continuity is when we're doing these limits, like the limit as x goes to 3 of, let's say, x squared minus 2x plus 5. Oftentimes we just plug in the point, and students get confused and think, oh, you just always plug in the point to find the limit. But that's not really the case, right? So this is 9 minus 6 plus 5, which is equal to, what is this, 3 plus 5, which is 8. The reason we can plug in 3 in for x is because this function here is continuous. And so we're really using the statement, how do you evaluate a limit of a continuous function? Well, a function's continuous, then you simply plug in the value. Plug in a. and look at this f of a, because that's what it's actually equal to if it's continuous. Right, so if f is continuous, right, continuity basically tells us how to find limits. And now most of the functions we deal with are continuous at this point. And then sometimes we run into these troubles, though, these trouble areas. The limit as x goes to 3 of like x minus 3 over x squared minus 9. In this case, we try to plug in 3, but you should realize it's not continuous at 3, so something's going to go wrong. So when you plug in 3, you get 0 on top, and you get 9 minus 9, which is 0 on the bottom. This is where we get this indeterminate form. Right, so we have an indeterminate form. And what's really happening here, if you look at the graph, is that you actually have a hole at positive 3. So it's not continuous there, and so of course you can't plug in 3 and get out the answer, so you have to do a little bit more work. And so for this one, hopefully you remember that you just basically factor top and bottom, so x minus 3 can't be factored anymore as given, really, and so then at the bottom can be x minus 3 and then x plus 3, and so this is when the x minus 3's cancel, and so that's actually equal to the limit as x goes to 3, and realize we can cancel these x minus 3's because we don't care what happens at the point itself. So the limit only cares what's happening around it. So it allows us to write this equality here and cancel them off and write down here x plus 3. Now we plug in 3 and we get 1 over 6. Right? 3 plus 3 is 6. And so we see the answer is actually 1/6, which is just basically saying that there is a hole in this function right here, and the height of the hole is actually 1/6. That's the idea. So from the left, it's going to be 1/6. From the right, it's going to be 1/6. You'll have a hole actually at 3, but the limit then is the same as the limit from the left and the right, so 1/6. All right, so that's really why we can plug in a number when we try to evaluate a limit. What is a limit? The definition, I don't expect you to memorize. It would be great if you learned how to kind of use it a bit. The limit laws are just sort of a fun activity. Sort of good exercise for you to go through mentally to understand if this, then that, if this, then that. And the squeeze theorem, it just tends to pop up a lot in various areas of mathematics. It's just a nice idea, so I like to introduce it to you at this time. So when you see it later, it's not so threatening because it's really a simple idea.